This is Chem Inquiry number 1, Fun with Metals and Alloys. And this is part 1, alloys, experiment number 1, copper to silver to gold pennies, formation of an alloy. So right here we've got 3 copper pennies that were minted before 1982 because they are minted with essentially solid copper. Pennies that were minted after 1982 have a zinc core to make them cheaper. So as we can see the dates on here, we've got a 1968, a 1978, and a 1980 penny. And in order to have it undergo the reaction that's next, first thing we need to do is to clean the tarnish off of these pennies. And to do that, we're going to put them in a solution of just vinegar and sodium chloride. That sort of softens the tarnish so that we can easily later take an eraser and just clean them up. So I'm going to just take these pennies, we'll plop them in here. A little swirl. We're going to let them soak for a little while. Actually, I don't know if you can see it, but they already look a little bit cleaner. So we'll come back in a few minutes and finish cleaning them off with an eraser.
A few minutes later.
So now we've let the pennies soak for a while in the vinegar and salt solution. So you can see some of the tarnish has already started to come off. They look a lot shinier. And then now that it's softened up, the last step is just to take an eraser and rub it against the penny. And so we'll try and clean this up a little bit here. So there's half. I think you can see how shiny it gets. You can clearly do this at home if you're really interested in having shiny money. So we'll just do this for the remainder of the pennies, and then we'll move on to the next step. So now we're on the second page of the lab, and the next step here is to do the alchemical transformation, the dream of the alchemist of yore. And that is to transform a more base metal like copper into something that is more valuable, like silver and gold. And so we're going to do some chemistry magic. I'm going to take 2 of these pennies and put them into this solution that is sodium hydroxide, and that 1M in front of there just represents how concentrated the sodium hydroxide ionic compound is dissolved in the water. And we've mentioned this before, that is 1 mole of sodium hydroxide dissolved per liter of solution. So that's the liquid in there, and then we've got some zinc. This is just powdered granulated zinc metal, pure zinc metal, nothing more than that. And that's over here on a hot plate. This aluminum pie tin is just to kind of keep the spills from getting everywhere. So I'm just going to drop a couple pennies in here, and it's heated up. And we have to let that sit for a while. Just going to give them a little stir here. And as they sit, we'll do a time lapse, but I think you can see there's some transformation starting to occur already. You can see got some magic happening here. Not quite done yet. I'm gonna let them just cook in our magic elixir for a little while longer, transforming those copper into silver. And while we're at it, here's our reference penny. See the difference? So we're going to let this go for a little while longer, and then we'll move on to the next step. think we're done. So we've done one step of our alchemist transformation. We have converted copper into silver. So the next step, I just need to rinse these off. A little bit of water. I'm just going to drop them inside this big old beaker of water. So that way I don't get sodium hydroxide all over myself. So let's just examine so you can see the transformation. So we have one more transformation to do, and that is to turn one of these pennies into gold. So let's go do that. Now the last part is to turn one of these pennies that are silver into gold. And to do that, of course, we need some fire. So we've got a big burner here, and I'm going to take one of these silver pennies and we'll heat it up in the flame. Every good alchemist requires flame. So you can see that. And there we have it. Copper, silver, and gold. So, of course, we didn't really transform copper into silver and gold. If you read the background, what we really did was to take copper in the penny. When we put it into the zinc and sodium hydroxide solution, we actually put a coating of zinc metal on the outside of the copper. So that's called plating it, in another way of speaking about that. And then the last step is we want to create an alloy. So just imagine we've got this coating of zinc on top of the copper, and when I put it into the flame, what happens when you put something in a flame or heat it up? Well, the molecules start jiggling a lot faster. And if this hand represents the copper penny, and this hand represents atoms of zinc on the surface, when we put it in the flame, they jiggle more, and eventually they kind of migrate into each other. And then on the surface of the penny, I would have a mixture of copper and zinc that is mixed together, which we call a solution, a solid solution of copper and zinc, and that's called brass. And so brass is what looks like gold. So we've got an alloy of brass on the outside. So we really didn't do a chemical transformation, we just created an alloy in a really fun way. This is experiment number 2, preparation of the bismuth and tin electrical solder. So we're going to make another alloy. You can read about how it's used in the lab manual. So let's just take a look at what we have here. The original metals that we're going to use, I've just got some samples of down here. This is bismuth. And if you watched an earlier video where I went through metals and ionic compounds, I showed you some bismuth. But that is bismuth, and this is a rod of tin metal that we cast at another time. We're going to take those two and melt them together in this gigantic crucible. Now normally when you do this in lab, you would be using about 1/3 of the amount that we're going to use, and you would use a tiny little crucible, just a ceramic little cup that is very heat resistant. But we're going to do a little bit more. We have this much larger crucible that we're going to melt the materials together in. Then once they're molten, we're going to go over here and pour them into little molds and make little trinkets. So here we've got our ingredients that we're going to use today. These are 3 times the amount that are listed in your lab manual, just for better visualization purposes, but the ratio is the same. It's 58% by mass bismuth and 42% by mass tin. And that gives us a particular type of bismuth and tin alloy that has properties you're going to investigate in the next part. So let's go ahead and we're going to crank this hot plate up to high. And I'm just going to add these into here. So it will take a little while for it to heat up. I'm going to mix them together with a glass stirring rod. So we just have to wait a little while.
A few minutes later.
So here you can see that we have the metals have melted and I've mixed them together. And this is actually the molten form of that alloy. Alloy is just a homogeneous mixture of the metals. But actually there's a really cool thing happening. You can see there's kind of this crusty layer on top. That's because we're heating this out in the open air, and the surface of the metal here, which is really hot, is continually oxidizing. It's reacting with oxygen from the air to form a ionic compound called, well, bismuth oxide and tin oxide. And in the metallurgical industry, that's called slag. And I'm kind of scraping that off the top, but watch what happens as I scrape. You can see the shiny surface of the metal underneath, and we just watch this for a second. You can see the color transformation. Just watch it. Now it's getting kind of golden. And one of the neat things about bismuth metal is that the oxide layer that forms with bismuth often produces all sorts of neat colors due to the different thicknesses of the film. So I think you can see now it's getting kind of a beautiful purpley glow. But I don't want to waste all of my alloy. I want to cast that into those little molds. So let's go and try that. So now let's take our molten alloy and we're going to try and make at least one mold. Hopefully we'll have enough to make two of these little critters. Oop, there's one. I'm not very good at pouring. So we got 1.5. We have to let that sit now and solidify. And then we'll take a look at our little animal that we created. Now we're going to do the testing of the alloy and compare it in terms of its hardness and melting point compared to the original metals that it came from. So you should remember to be recording these observations in your report sheet. Right now we're going to do part A, the hardness testing, and after that we'll do part B, the melting point. But make sure you record your data and observations on the report sheet as you watch this. So the first thing I want to do is pop our little guy out of here. Oh, it's pretty cute. So we have this little alloy, a little trinket. So that was fun. Now you know how to be a jewelry maker. So in the next part, what I'm going to do is I'm not going to use this particular little cast bismuth tin alloy. I'm going to use this one that's already prepared to do the testing. And so here, now to do the hardness testing, what we do is we're going to take each one of these and try and see if it can scratch the other metals. And so the one that is harder in terms of the hardness of the metal is the one that can't get scratched. So for example, let's take our bismuth and tin alloy that we cast here, and I'm going to try and scratch this on tin. We're going to see if this bismuth and tin alloy can scratch tin. That would mean that tin is softer. So let me see if I can get in here and make a scratch. Well, you can see that dent in there. So you can see the angle that I'm scratching. I'm making all sorts of marks. And I can try this with the bismuth and tin alloy. And I'm going to take the tin and see if I can scratch this just to kind of double check, see what happens. So rub it on there. I really can't make a dent in the bismuth and tin alloy with tin. What does that tell me? That tells me that the alloy is harder than the tin metal that it came from. Well, now let's do a comparison between the alloy and bismuth metal. So we'll take the alloy again. I think you can see the scratches that I made up at a diagonal. So apparently the alloy is even harder than the bismuth that it came from. So just kind of get in there. And just to double check, I'll take this piece of bismuth and see if I can scratch the alloy. Nothing. In fact, I started to flake some of the bismuth off. So now we can see one of the reasons why we make an alloy. It's harder than the two original metals that it came from. In the next part, you can see how the melting point of the alloy would compare to the two metals that it came from. But now we have to do one more test. I have to see which one's harder, the tin or the bismuth, so that we can rank them in order of hardness. So I'll just take a tin here and see if I can scratch this bismuth. I'll do it down here. Not really getting any dents in there like I could with the alloy. Let's double check, take this bismuth, and I'm going to try and scratch this tin. And I think you can see right here that we've been able to make some marks into the tin. So bismuth can scratch tin, but tin cannot scratch bismuth. So in your data sheet, you should be able to rank in terms of the hardness of tin bismuth and the bismuth and tin alloy. So now we're going to do the part B of testing the alloy. This is the melting point test. And we just want to see if we've changed the melting point at all by making bismuth and tin form an alloy together. So what we have here on this glass watch plate are small samples of approximately the same size of our three metals. So right here, this is tin, and here we've got a little piece of bismuth, and this is a piece of the alloy that we made and just cut into a really small chunk. And so they're about the same size, and what I'm going to do is turn the heat on to high, and as it heats up, I'm going to kind of poke at it to see which one is melted first. And so what we want to do is get the order in which they melt. The one that melts first has the lowest melting point, and the one which melts last is the one with the highest melting point. So there we can see our alloy has melted, but bismuth still pretty solid, tin still solid. The first one to melt is the alloy. tin has become molten. Bismuth, still solid. So we're just starting to get some bismuth be molten. There we go. So we have our order. The alloy melted first, then the tin melted, and then later at a higher temperature, the bismuth melted. So now we are on part 1, observation of crystal grains. I'm going to show you a short video for part A, the video background, and when you're done, we'll continue on for the observation of galvanized iron. This is a short part of a clip of a YouTube video by a person named Steve Mold, who's got a great YouTube channel. I highly recommend you checking it out. Some really interesting stuff. But we're going to watch just the first segment of this to discuss some background about what a crystal grain actually is.
There's this really cool desk toy called Atomics that you can't buy anymore. So a couple of years ago I made my own. It's about 3,000 ball bearings sandwiched between 2 layers of acrylic. They're free to move in 2 dimensions, and they naturally fall into this regular lattice structure, except that there are imperfections in the lattice. And actually that's why I built this thing in the first place, because I wanted to make a video about lattice imperfections in things like diamond or metals, and this Atomics toy is a really good model for that. If you want to watch that video, the link is in the card and in the description. But someone commented on that video saying that this Atomics toy might also be useful for demonstrating what's going on when you heat treat metals like annealing or tempering, and that's what this video is about. If I allow the balls to fall quickly into position, they form these small regions of regularity. You get the same kind of arrangement in the atomic lattice of metals, these small regions of crystalline metal that are neighbouring each other. And they can't form one single crystal because they're oriented differently. These regions are called grains in a metal, and it turns out that the size of grains in a metal really has a profound effect on the physical properties of that metal.
So part 2, experiment number 3, where it says part 1, observation of crystal grains. We're in part B of that, and that is an observation of actual metal crystal grains, or little crystals. So we're looking right now at a piece of galvanized iron, and that is just a sheet of iron that is, when processed, dipped into molten zinc. And when that thin layer of zinc solidifies as it cools, it forms individual crystal grains. And so right here you can see little individual shapes as we're zooming in more. There you go. Every one of those little irregular shapes is kind of a macro-sized crystal. You normally can't see this with most metals, but zinc just happens to be a metal that, when it's solidified on a very thin layer on another metal, it forms these large-sized crystal grains. And so, you know, you can go down to the hardware store or wherever and buy galvanized iron, and you'll actually be able to see these with your naked eye. But it's really kind of a beautiful pattern. Each one of those little geometric shapes is a uniform, pure crystal of zinc. And kind of see if we can play with the light a little bit. And you can see the differences, just the light reflecting off from different angles. Gives you a little bit of a different view of those crystal grains. So try and make a sketch of that and record your observations on the report sheet. So one question that we could ask is, what about our alloy? Could we see the grains on our bismuth tin alloy that we made? And so it actually turns out the answer is no, not with the naked eye or even under a magnifying glass or even a very powerful light microscope. The grains are just much too small to see that way. In addition, as you're about to see, the mixtures, which an alloy is more complicated than a pure substance. So when you looked at that sample of galvanized iron, the zinc on the surface, that was just pure zinc. That grew into those nice large crystals. But when you've got a mixture, things get a little bit weird. So let's take a look, for example, at the alloy that we had. So we have a small electron microscope called a scanning electron microscope. That just means that an electron beam scans over the surface to make a picture, sort of like an old style TV tube used to do. I'm not going to go into the background of how an electron microscope works, but I will talk about some of the pictures we took. So I had a former student who was working on a research project with me a couple of years ago, and she took some pretty neat pictures of these alloys for bismuth and tin. So this first image that you're looking at is the surface image of a bismuth and tin alloy. And one thing about scanning electron microscopes, they sort of look like a picture you would see using light. But as you're about to see, that's not necessarily true. These are images that are made according to the intensity of the electrons as they hit the surface and are reflected back after colliding with the atoms that are inside the material. So this, if you look at the bottom down here, it says topographic mode, like the topography. What's the surface topography or the surface roughness? And this doesn't look really that interesting. I mean, it's kind of cool to look at. This is a surface magnification of 1,000 times. So down here where my cursor is kind of circling, this gives us an indication of the magnification. So this is times 1.0K, so that's 1,000 times. And if you were in my lab last term, you did a question at the end of one of the labs where you had to look at a scanning electron microscope image of a CD and a DVD. And you had to use the scale at the bottom. So this whole scale going from the left-hand side to the right-hand side is 100. That's micrometers. So each little division is 10 micrometers. So 10 micrometers is 10,000 nanometers. So while this is pretty small, it's not super duper small. We're not down to the level of individual atoms yet. But basically just what you're looking at here is sort of like if you looked at the frozen surface of water, there'd be all these different variations in height and things like that, and just sort of random. But I pointed out here in the upper right, there's something I want you to focus on. And if you can see, there are these little sort of rectangular boxes sort of aligned next to each other in some locations that I'm kind of pointing out here. And you can kind of see that in some other locations in this image. So that actually turns out to be a really relevant point in terms of the crystal grains that this material has. And so what we need to do is we need to change the way an electron microscope looks at the material that's in it. So again, this is called topographic mode, but we can change the setting, that the way that an electron microscope works, and we can actually get what is called compositional analysis. And so this next picture, it's not the same image, but it's another picture we'll take a look at here. Oops. And so these aren't the world's most perfect images, but I think you can see some differences here. Now we're looking at roughly the same magnification. It's the same piece of metal, and it looks quite different. And so this is what is called composition mode, and I'll explain that in a minute. But I just want to have us take a look at some of these pictures. We're going to increase the magnification. So what you're looking at, the light and dark regions, are actually crystal grains. So remember, this material is a mixture. It's an alloy, and the composition that of this particular sample was 67% by mass
bismuth and 33% by mass tin. That's different than the one that was prepared in the lab and in the video. I'll have some of those pictures in a minute. But we just happen to have a variety of these pictures I wanted to show you. So the little regions down here, they look a lot different than the crystals of zinc and the galvanized iron that you saw. They have these little kind of long, drawn out regions and alternating, kind of like a sandwich. And this is pretty typical of alloys, of two component alloys, meaning alloys made of just two different things. And but it doesn't all look exactly like that. You can see there are some regions over here on the left where the crystals are a little different crystal structure. So I just want to zoom in. So right now we're at about 1,200 magnification. Again, this is not the topography. You couldn't see this with visible light. It wouldn't look different color, like the whole surface just looks silver. But an electron microscope has a way, I'll explain in a minute, of detecting the different composition of different regions on the surface. So that's 1.2 thousand times. Here's just another location on the surface. So how these things form depends upon the way the material was cooled. And so we can see it's really pretty interesting. There are these dark regions that are kind of uniform, and then there are all these kind of squiggly parts, and they alternate back and forth. So let's just look at a couple more. Let's zoom in a little bit. Here we're even closer. This is 25,000. Sorry, 25,000. This is 2,500 times magnification. You can kind of keep an eye on the scale down here at the bottom too, and it always tells you what it is. Let's go even further. We're going to go to 3,000 times. This is a different region. So it seems irregular, but then there are all these regions of sort of semi-regularity. So let's go down. This is now at 4,000 times. So this is about 4 times as magnified as the very first image that you saw. And you can see some topography here. You can see sort of the surface unevenness. And then the different colored regions, again, are not topography. They are compositional differences. But kind of neat, each of those little regions are different little grains. And so there's a variety of sizes. So mixtures are complicated in the way that they solidify. So what are the dark and light grains in this sample? And here's the thing about this setting on a scanning electron microscope and SEM. It actually turns out that the darker areas are lighter atoms. So they have a lower atomic number, and the lighter or brighter areas in an image are produced by predominantly heavier atoms or have a higher atomic number. This alloy is composed of tin and bismuth, and if you take a look at their atomic numbers over here on the right, we can see that tin, with an atomic number of 50, is much lighter than bismuth, which is atomic number 83. So from that, we just can make a prediction that the dark regions are going to be the lighter atoms. And so we should think about this when we look at the remaining pictures. I'm going to show you the dark areas should be rich in tin, and the lighter areas should have more bismuth in them. When we did the lab, we just assumed that these two things just mix together when they form an alloy and make a homogeneous mixture. But at this level, at the microstructural level, it actually turns out things are a lot more complicated. They don't seem to want to mix together. Tin likes to hang out with tin, and bismuth likes to hang out with bismuth. And so you get these regions of separation. But even that's not the end of the story. Even these mixtures, even these light and dark regions are themselves mixtures. So they're not, for example, the dark regions are not essentially 100% tin, and the light regions are not 100% bismuth. But as it says down here at the bottom, the light grains, the light regions, are what we would call bismuth rich. They're a very high percentage of bismuth and a low percentage of tin. And the dark regions are a low percentage of bismuth and a high percentage of tin. So we might want to ask ourselves, is there any way to verify our prediction of what elements or what percentages of those elements are in those different grains, those different colored grains in the electron micrograph. So there is, and it's a technique that's kind of similar to something we talked about in Chem 221 called photoelectron spectroscopy. And it's called energy dispersive spectroscopy, or EDS. And I just want to give you a little background on what that is before I explain what we're looking at here. And I'm just going to kind of refer to what's over here on the right-hand side of the screen. So it is similar to photoelectron spectroscopy. And so here's what happens. Inside an electron microscope, those same high-energy electrons in the electron beam, instead of making an image from them, we use them to knock out what are known as the core electrons in an atom. So imagine your vision of an atom. Let's go back to an even simpler vision of the shell model. And we've got these electrons existing in different shells, different layers from the nucleus. And when a high-energy electron from the electron beam in the electron microscope crashes into the sample, they're energetic enough that they can sort of drill down into the core electrons of an atom and knock one of those electrons out. Now, that's not what we're looking for, actually, the removal of that core electron. In this way, it's sort of like photoelectron spectroscopy in that those electrons could be removed, and we could, if we wanted to, in another setup, measure their kinetic energy and from that determine the ionization energy. But that's not really what we're looking at here. It's a little bit easier to do this next step, and that is that a higher energy electron, an electron in an outer shell of the atom, will fall down and replace the core electron that was knocked out. And so you know that when electrons fall from higher energy shells to lower energy shells, they emit energy in the form of a photon of light. Well, it just turns out for these larger elements, when the outer electron or one of the outer electrons falls back down into an inner shell hole that was left by an electron that got kicked out, the photons actually correspond to X-rays. And that seems extreme because we learned in 221 that jumps that happened in hydrogen and the other elements, those gave off visible light. But actually, we never really pursued it too far. And it turns out that the larger the nucleus, the lower the energy of the inner core electrons. And that jump to get down into that lower core is actually more energetic than visible. It's a little bit more energetic than beyond visible in the UV and into the X-ray region. So these regions, UV versus X-ray, there's not like a hard line defining the difference of them. And so sometimes they are UV photons that come out, but for the heavier elements, it's almost always an X-ray photon. Well, all we have to do is capture and measure the energy of that X-ray photon, and that is characteristic of every particular element, right? Every element has its own series of shell energies, and all the jumps in between shells for different elements will be different. And so what you see on the right over here is what's called the EDS spectrum. So the computer has labeled this for us already. I didn't have to identify it. That would be tedious. But we can see like this peak right here that I'm highlighting. That corresponds to an X-ray photon that was emitted by an electron in a bismuth atom falling from a higher shell down to an inner core shell, and that electron was emitted. And so, similar to photoelectron spectroscopy, the height of the peak is proportional to how many of those X-ray photons that were emitted. And so, there's a couple things you would calculate. The more particular bismuth atoms there are, we might see more X-ray photons of bismuth at this particular wavelength. So here's another one that is labeled as tin. These green lines, you can just ignore them. Those are just to help me identify what the elements were at those different peaks. But you can see that I've only shown part of the spectrum down here. There's a couple different peaks for bismuth over here, and there's a couple peaks for tin. And those are characteristic of those particular elements. So only bismuth gives a peak at that particular X-ray frequency or X-ray energy. And so once that has been programmed into the computer, it's really easy for it to try and give an identification of what the elements that are present that might be giving off those X-rays. It's really pretty cool. So what's on the horizontal scale? So this is really would be a scale of photon, X-ray photon energies, but it's not really listed. It's not important because, like I said, the computer is doing all the hard work for us. It's just sort of pattern matching. All right, so now we have a very convenient way, an electron microscope, to figure out what the elemental composition of a particular sample is. And so what we're looking at in this picture is one of the microstructures of the bismuth and tin alloy. So up here, the red arrow points to this box, and in that box are two crossed white lines called a crosshair. And right at that center is where we shine the electron beam in particular to produce those X-rays. And the collector in the electron microscope collected them, and it's going to tell us just exactly what is at that very spot at the center of that square. And so down here at the bottom, this is going to give us, it says the elemental composition. We've got the region is dark, and we predicted that that should be richer in the lighter element tin. And right over here on the right, it's a little bit blurry, but it says that this spot is about 54.6% by weight tin and 45.4% bismuth. And that does match our prediction, right? We said that dark areas should be rich in tin and have less bismuth. And that's what we see at this dark area. So let's take a look and see if we can see similar results in other places on here and verify our results. So here we're looking at a dark area right here, right where that crosshairs is. And you can see the spectrum. It's interesting, compare this to the last one. You can see that this peak in the last slide was really high for bismuth. And so there must have been a lot more bismuth in that sample compared to tin. And the tin peak is much higher. So if we go down and look at the percent composition down here, we can see that it's 92.8% tin and about 7.2% bismuth. So it does kind of correlate, right? The higher the peak, the more X-rays were produced, which you get from having more of those particular atoms in that sample. So this is a very tin-rich grain. Here's another one, another dark spot. And here again, you can see the weight percentage is about 94.5% tin and only about 5.5% bismuth. And there's much stronger peaks, much higher peaks for tin than there are for bismuth. Peaks are the same, they're just the heights are different, and that's how we get the percent composition. So I just want to show you here the fact that in each one of these three, that the location of the peaks is identical in the three different locations in the sample, but the height of the peaks might be different. So I can do this little trick in PowerPoint. I'm just going to take this one and slide it over. If I line it up just right, you can see that all the peaks are in the same place, but the peaks are of different height. So these two, the one that is on the right and the one that I'm overlapping in the middle, had very similar proportions of tin and bismuth. But what about the one on the left where it was bismuth and tin? Bismuth was a higher proportion than it was in these other two. Well, all that should be different is the height of the peaks. And if I slide that over there, so you can see the location of the peaks match, right? Those are characteristic of any particular element. The composition, which determines the height of the peaks, the percent composition, I should say, is different, but it's neat how it just exactly overlaps. So it is characteristic. It's a fingerprint spectrum. And that's how we can use that kind of spectroscopy to identify what those components were.
So this is the alloy that was made in the lab, 57% bismuth and 43% tin. This composition is actually it's got a very special name. It's kind of a funky name. It's called a eutectic. And that is the lowest melting point composition. So when we looked at the other composition, that was about 67% bismuth and 33% tin, that actually would have had a different melting point than the one that we looked at in this particular lab. And it's higher. This particular composition has the lowest melting point of any composition of bismuth and tin. So anyway, just some more pictures to take a look at here. We'll just scale through go through these. And so this is 3000 magnification. Here we're getting in closer, 4,000. These are not all at the same location, but kind of funky looking. Here we are at 5,000. You can see those different bands of the different crystals that are either bismuth rich or tin rich. So pretty crazy looking. 5,000 times magnification, something you just couldn't do with a light microscope. If you look at the scale down here, it's 20 microns across this whole scale, which means each little step on this scale is 1/10 of that, so that's 2 microns. And so 2 microns is how many nanometers? So there's 1,000 nanometers in a micrometer. You've got 2 micrometers. That's 2,000 nanometers. So this is pretty tiny. So I'm kind of, each one of these little steps is 2,000 nanometers. And so the resolution down here, one of these little lines here, these little rectangles of dark you can see I'm highlighting, I'm going to say that's probably maybe 1/10 or 2/10 one of these little boxes. And so that was 2,000. A tenth of that is 200 nanometers. So we're really looking at the very small scale. If I could get in another factor of 10, I might be getting down almost down to the atomic or molecular scale, but this particular electron microscope really can't get any better than that. So just another shot, just a different region. So when you look at most things in the world that are mixtures, they're very complicated. But I just wanted to show you some example of how we can actually look at some of the things we talk about in lab using an electron microscope that we have even here at PCC. And if we ever make it back to live teaching someday, you should come and talk to me and I could show you the electron microscope. And it's really easy to learn. This is part 2, the malleability and ductility of metals, looking at the metal deformation at the atomic level. And so this is in your lab manual, and that is down here on page L18. We're doing the part highlighted in yellow here, and this is trying to have us think about what has to happen at the atomic level when you deform a metal. What is the key to making them be very malleable and ductile? So what we have to do is go to the report sheet so that you can see what videos you're going to be looking at here and what data you need to collect. This is page L24 on the report sheet. Here you are at part 2, and it's just indicating here what are the different videos that you're going to be watching. They're just very short little clips. But don't forget to answer these questions when you get to this last video. So you might want to take notes in the margin or whatever, but just to give you some information about what's going on. The concept here is how do we deform a metal? And the thing to introduce to you, a new concept, is the property of a metal called a dislocation. That was hinted at in the early video when you were watching in the pre-lab about when they were casting the bell from bronze. These are irregularities in the crystal structure, and there's this little set of images down here. The first thing I just want you to notice right here where that little hand cursor is pointing, if you look at the lighter colored atoms, they're all in rows, nice and neat like a regular crystal, but then there's like an extra row or extra plane of atoms that have been inserted, and that's a dislocation. You can see that this row that I'm tracing out right now has been dislocated off to the right, and there's another row that has been dislocated off to the left. And it seems like an imperfection in the crystal, but actually that is the thing that enables metals to themselves be very malleable. And so we're going to see in a couple quick videos why that's true. So here are video number 1 and video number 2. Video number 1 is actually at the bottom, but the question is, we want to think about how much force would it take to cause a row or rows of atoms to slide past another row of atoms. So remember, atoms are connected to each other in a metal through these sea of electrons, these loose valence shell electrons connecting one atom to another. So if we want to slide one row past another, we have to do some bond breaking. And how much energy does that take to accomplish our goal? So actually we're going to look at the first one down here at the bottom it says animation of slip by movement of whole lattice planes. And so slip is the movement of one plane or row of atoms across another. It's called slipping, and it's going to happen on what's called a slip plane. You'll see that in a minute. It's very short, but just think about what has to happen, how many bonds have to break to enable this. So what you can see, in order to cause that to occur, we have to break all the bonds of the whole row. And it's not just, 7 or 8 atoms like it is here. It's billions upon billions of atoms all at once have to be broken in order for this to slide. So let's just take a quick look at that again. All those bonds are broken. The new bonds are formed, but the metal has been deformed. That is what we call slip. So video number 2 then is what we're going to see happens if you have a dislocation. And a dislocation allows you to slip a plane of atoms, but instead of moving them all at once, you only break 1 or 2 bonds at a time. It's kind of like the dislocation, that extra inserted line or row or plane of atoms hops along the crystal. And there's some good animations or some images in your report sheet to kind of take a look at to help you with that, but just watch what happens here. Oops. So highlighted in red is that extra row called a dislocation. So to accomplish the movement, it turns out that at any instant in time, only 1 or 2 sets of bonds have to be broken. So let's just watch that again. So you can see here the end result is the same. It's just a matter that in the bottom one, where the whole plane has to slip, the problem is you have to break all the bonds at the same time, requiring a lot of force, a lot of energy. But if there's a dislocation, then you only need to displace 1 row, 1 bond at a time. I can kind of move through this slowly. You see that we're only breaking 1 and it just sort of hops over. You can think of that as dislocation hopping. So that makes it much easier to deform a metal if it has this imperfection called a dislocation. This is video number 3, dislocation glide version 2. It's just another way to think about or visualize the slip or glide of one row of atoms across another by using a dislocation. So I think you can see here it's that extra row of atoms. It's just hopping 1 at a time, and the end result is that we see all of those rows move. We're going to watch the next video, and this is a interesting kind of video in the sense that what you're looking at here is just a snapshot from it as I introduce it. But this is actually a top-down view of a bunch of bubbles floating on the surface of water. And the bubbles, when they're packed in, arrange themselves in the same way that a crystal would in 2 dimensions. But what we're going to look for, and I've highlighted up here in the upper right, is I think you can see, first of all, before I talk about that, do you see the crystal grain boundary? I'm kind of tracing it out with my cursor right now. And you can sort of see that the alignment of atoms is different. Over here on the right is 1 crystal grain, and then down here on the bottom and to the left is another separate crystal grain. But in the crystal grain over here on the right, there is a little dislocation. Do you see the extra row of about 4 little atoms inserted between the 2 other rows that are highlighted in pink? And what I'm going to show you in the video, we're going to play it slowly at first, is that there's going to be a stress applied. In other words, essentially we're going to try and deform this crystal. And I'll show you in a minute, though, this dislocation is going to work its way over and allow the crystal to deform until it gets to the grain boundary. And then because the alignment of the next grain is different, that dislocation can't move anymore, and it gets pinned down at the grain boundary. We call that dislocation pinning. And because the dislocation can't move anymore, the crystal can no longer deform. And we'll talk about what that means in terms of the strength of the material in just a minute. So let's go to that video. So that dislocation I was talking about, it's up here in the upper right. It looks like these 4 atoms. And it's not the world's greatest movie, but see if you can follow what happens. This dislocation is going to travel sort of down and to the left. And I'm going to play the first part of this very slowly at first, and we'll speed it up to normal speed. Let's just keep an eye on it. It's very slow, but now it's traveling down. You can see a bit of a deformation along this line. Keeps going. Hits the grain boundary. The atoms aren't aligned correctly anymore. Nothing happens. So let me reset this, and we'll play it a little bit faster. So just sort of keep your eye on this. You see it sliding down? Boom, and it gets down here. Can't go anywhere. And they're just applying more stresses. See if you can see some more movement. It's hard to catch, but things are moving around. I'm going to reset it again, but this time I'm going to play it at regular speed. You can see it traveling up there. So it's kind of squeezing on this thing, but for the most part, it doesn't move. Here is another set of bubbles, and I'm just going to play this at regular speed maybe a couple times, and you should be able to see dislocations zipping around as this is being deformed. I'll just kind of pause for a minute and see if you can just find any dislocations in the crystal lattice before we start. Can you find a crystal grain or any irregularities? All right, let's take a look at it. It's hard to catch them in movement, but they're just sort of zipping back and forth. Play that one again. They're like little ripples that travel. And there's a really nice image of the inchworm on page L24 in your lab manual that serves to illustrate that. So now on page 5 of the report sheet here, on the next page after looking at those videos, there is an observation that says a sample of metal with many tiny grains and lots of grain boundaries is known to be much stronger and harder. It can't deform than a similar piece of metal with few or only one crystal grain. So your job is to use what you've learned from those previous 5 videos to try and explain, propose an hypothesis down here. It says propose an explanation as to why it's much more difficult to deform a metal with many small grains compared to a metal with larger or fewer grains. So there's a clue there. It says, what did you learn from those 5 videos about how dislocations move when you try to deform a metal? And what happens when they hit a grain boundary? That was the subject of the last couple videos. So if there are lots of grain boundaries, does that help you deform the metal, or does it decrease your probability of being able to deform the metal? And so when you answer that, you should discuss what happens to that little dislocation as it encounters a grain boundary and why that would be good for or bad for your ability to be able to deform the metal. Now we moved on to part 3 on page L18 of the lab manual, and that's called the cry of tin. This is a very old phenomenon that has been noticed back in even medieval times, and it's just a very strange thing. They didn't understand at first what was going on, but it says some metals such as tin are deformed. If you twist it or bend it, sometimes you can get multiple planes to shift, not completely, but just sort of stretch and get out of place all at once, sort of like a snap. And in fact, that little snapping action, as you can see, I'm going to show you a quick animation of this, going from the left picture to the right, as you bend it and deform it, actually creates a whole bunch of little atomic scale sonic booms all at once, and you can audibly hear that out loud. And we're going to have a video of that in just a minute here. We're now on part 3 here on page L25, the cry of tin. And this is the report sheet, so it just says follow the instructions on page 4 of the lab, which you're going to watch in the video, and then just report what you hear. Here's a quick animation of what's going on and what might cause that noise. So just kind of we'll play this video a couple times. So it's that quick snap as we break bonds and new bonds are formed, that moving that causes this thing to sort of make this noise. That's called the cry of tin. So we'll switch over back to the lab video and you can see examples of that.
Part 3, the cry of tin. So we've talked about the introduction, about what that cry of tin is, and now we're going to take a look and see if we can actually hear it. So we're looking right now at 3 bars of tin that we've cast, and it's kind of dark because we had to try and find a place where there was little noise, and the lights that we turned on, the fluorescent tubes, were crackling as they heated up, so we turned the lights out. So that's why you can't really see anything, but that's not important. The main thing here is to give a good listen. And so each one of these bars, I'm going to take them and one by one bring them up to the microphone of the camera and listen very carefully to see if you can hear. It sounds kind of like a crackling sound, and that are the little sonic booms of the metal crystals snapping past each other. So here we go. I'm going to take one. We'll see if we can listen. You might want to turn the volume up on your device. So I'm not sure how these might work, but one of these will give us some crackles. That's a good one. So if you could hear that crackling sound, that's what they call the cry of tin.
So on page L25 of the report sheet on part 4, hardening metals by creating an alloy. So it mentions there that you should have noticed that the bismuth tin alloy was actually a lot harder than either the original bismuth or tin metal that it came from. And if you paid attention to the pre-lab video where they were casting the bell, they sort of explained the idea that making an alloy where you've got atoms of different sizes makes the alloy harder. And so there's lots of reasons why that could be. This one is not about dislocations, but I do want to show you a quick little video clip, and it doesn't relate to an alloy per se, but if I flip over to that video page, if you take a look at this right now, I think you can see that in a nice closely packed set of atoms or spheres, you can see there's 2 different lines there, and those lines are not as smooth as the other one is. In other words, they have different levels of smoothness, and so if depending on the angle in which you try to deform the metal, it's going to run into more or less resistance. And so let me just animate this for you and see if you can see which pathway offers the path of least resistance. So you can think about which would require less work or less energy to have atoms slide along. So sometimes the bumpiness of the path can determine how difficult, and by difficult we mean how much work it takes or how much energy it takes. So which of these paths do you think resists deformation the most? Sliding along the diagonal path or sliding along the horizontal path? So as we go back to this, you should then try and put that concept together. And down here it has you think about which one of these representations of that bismuth and tin alloy really represents what you're looking at. And here we notice that We've got the atomic radius of tin and the atomic radius of bismuth. So they're different from each other. One's larger, bismuth is a little bit larger atom than tin is. And so which one of these represents the mixture that you made? And what you need to really answer this question is to go back, and it says considering the percent composition of the alloy earlier in the lab. And they weren't equally mixed 50-50. And so which one of those two elements is in higher proportion? And that would lead you to which one of these two. It says circle your choice. And then the last thing is for you to kind of put it together to hypothesize why it's much more difficult to deform an alloy along planes that have these sort of mixed size atoms in them. And so that was based on looking at this video that you just saw. Now we're on to the last experiment, part 3, the heat treatment of iron and playing with phases. So that's instructions are on page L19. You should follow along and think about the explanations that are given here as you watch us carry out this part of the experiment. It's really pretty cool. And then as you're watching the experiment, there is a location on the report sheet on page L26 coming up here that you should record those observations up here at the top of what the metal is like and what's happening, what you observe. So remember, you're not just kicking back and relaxing and watching the video. It's pretty cool, but your job is to act as the chemist and look at the observations here. You know, what's happening to the metal, what does it look like, things like that. So just make those observations, and then we'll just afterwards come and finish up and talk a little bit about this analysis and extension. And I do have another little explanation video clip at the end to help you understand what happens in this heat treatment of iron.
Part 3, heat treatment of iron, playing with phases. This is experiment number 4, the heat treatment of iron. And here we've got 4 bobby pins. These are just made out of iron, and we've snipped off that little plastic nub on the end of them so that it doesn't catch fire and stink up the place. And what it says to do in the instructions, first of all, we're just going to take a look and see what this metal is like. It's all kind of springy, very stiff. That is important because if you want it to clamp onto something and hold your hair in place, you don't want it to be soft and malleable. But what we're going to do by heat treating it in the flame is show you that we can change the stiffness and malleability of these bobby pins. But the first thing we have to do is to straighten them out. So we're going to do that right now. All right, so now we've got our 3 pins that are straightened out, and we're going to each heat treat them, each one a little bit differently. And the first one is called the annealing of iron. And we're going to try and get this whole pin to be red hot. And so making it red hot, we're not going to melt it, but making it red hot just it allows the atoms to sort of move around. And we're kind of actually allowing those crystal grains to not really melt, but be able to rearrange themselves in the solid phase. And so we're going to heat that up to glowing red hot, and I'm going to use a tongs for that. And these bobby pins apparently have a plastic coating on them to make them smoother and protected from rusting. So that's burned off, so now we're just going to heat this up. I think you can see we're getting it nice and red hot. So the first stage in heat treating iron is to get it to be red hot. cool very slowly. Set that in the background here. All right, so we've got 3 pins that are all treated the same way. And then we still have our original one over here. And we're going to pause for a minute to let those pins cool down. And we're going to bend them into an S-shaped hook. Now that the wires have cooled, we're going to see if we can detect any differences in their hardness or malleability compared to the original bobby pin. So remember, this bobby pin is very springy, and you want that because you want it to clamp together and hold your hair in place. So it's very, very stiff and springy. And now, if I look at this bobby pin here that we have treated in the flame, and that's called annealing, where you heat it up to red hot, and then you just let it very slowly cool so that the atoms have time to move into new arrangements where the crystal grains are larger. And this is just very soft. And I'm going to bend this into an S-shaped hook, like it says in the instructions. Just really easy to do. It's just very soft and not springy anymore. So by doing this heat treatment, again, the steps are to heat it. You got to get it red hot and let it cool slowly, in case you want to do this at home. So now we've got 3 pieces of annealed iron, very soft. And the next thing that we're going to do is I'm going to take one of these annealed pieces and heat it up again until it's red hot. At that point, I'm going to do what's called quenching. And we're going to dunk it into this water, and it will very quickly cool down. So fast that the atoms can't rearrange themselves into those nice perfect crystals anymore. So I'll grab this. So again, we got to get it up to that red hot stage. And now I'm going to quench it. I'm going to burn myself, but get that out of there. So this is called hardened steel, hardened iron. And it's very springy. And it's brittle. So when you have metal, if you make it stiffer, it also becomes more brittle. So we've got 2 extremes here. We've got this very springy steel, which is good. You can make springs out of this material. It's sometimes called spring steel. And it originated from something that was very soft. It's not as springy. I can just bend this around, very malleable. So that's the second part. That's called hardening. Now the last part is that I want to take another one of these, and I'm going to go through the hardening process again, but then I'm going to do what's called tempering. And tempering means to heat it up very gently in the flame after it's been hardened, and not get it red hot. We don't want it to be completely annealed so that it's all soft, but I want to get it kind of somewhere in between. So I'm going to take this nice annealed piece of steel, and let's get it red hot again, and then we're going to quench it. Make it very, very hard. And so while we're doing this, just thinking about why that iron was so hard after being quenched. Well, right now, when it's in this red hot stage, all those iron atoms are jiggling around, and it's very disorganized. The many, many tiny little crystal grains and imperfections in the crystal. And what I do when I quench it, I'm going to kind of freeze them in. So now you've got this metal that is all disorganized. And so because there's lots of those dislocations and lots of little crystal grains, it's very difficult for the atoms to slide past each other when you're trying to bend it. Which means that, as I showed you earlier, instead of bending, it'll just break. But now we're going to temper the steel. And that means to just slowly heat it. We do not want to get it red hot. All we want to do is give the atoms just enough little energy so that we can get crystals to grow again. And I don't know if you can see this, but it starts to look kind of a blue color. And that's just right where we want to be. That sort of bluish oxide coating. It's not red hot, but it's getting just warm enough, making some tempered steel. So we should be there. I'm going to set this down. Let it cool. So while that's cooling, just to review what we've seen so far. We've got our original bobby pin, very springy. We had up here our first annealed piece, which was very soft and bendy. The second part was, remember, we hardened the iron by heating it red hot and quenching it, and that left us with this very disorganized at the molecular structure, super brittle, just very hard, but brittle. And so hopefully now, this piece should be cool. If we can see, there's kind of a bluish tint on there. So this hopefully will be somewhere between the very, very hard nature of the hardened steel and the very, very soft nature of the annealed steel, or I keep saying steel, iron, same thing. But as you can see, I think you can see, ooh, a little bit stiff there. I can bend it, which I couldn't do with the other one. It's hard for me to show you. It's a little bit less springy. If I bend it, it deforms a little bit. Not as springy as it was before. I'm sure I can get in the shot. But definitely not as brittle. And so we can play around with those different heat treatments. I can change the degree of the tempering that I do to leave it a little bit harder and stiffer, springier, or I can continue to heat it longer and make it a little bit softer. So this was one of the first sort of metal treatments that were discovered centuries ago. And it was how people were able to understand how to change the properties of iron and steel, making it harder or softer, most notably in like farming implements and swords and things like that. So they didn't really understand at the atomic structure what they were doing, but they did realize that if you did these heat treatment techniques, you could change the properties of metal and without having to do any sort of chemical reaction to them.
So let's go back to that steel ball video by Steve Mould and see if we can understand what happens when the heat treatment that you saw at the atomic scale. Pretty interesting.
So let's see what happens to the grain size when we heat treat a metal. This is a model of an atomic lattice, so we need to think about what heating means for the model. Well, on the atomic scale, heat is just kinetic energy. It's how much are the atoms and molecules jiggling around. So if we want to increase the temperature in our model, we need to jiggle the balls around. I'm going to jiggle these balls with a vibration generator, which is basically a speaker with a prong. And because I'm filming at 50 frames per second, I'm going to try vibrating at 50 Hertz and 100 Hertz. By picking a multiple of the frame rate, I don't need to worry about the stroboscopic effect. You can see how the added kinetic energy gives the lattice an opportunity to rearrange itself. That extra movement means that the atoms can slip and slide into new positions, and the grain size increases. So heat treating a metal lattice in this way increases the grain size. But what effect does that have on the physical properties of the metal? Well, in metallurgy, you have all these different terms for the physical properties of a metal. Hardness, toughness, strength. They all sound really similar, but they all have different technical definitions that I don't want to get into in this video. So we're just going to gloss over all that and say, how hard or easy is it to bend a metal permanently out of shape before and after heat treating in this way? Well, my assumption would be that if you have larger grains, larger crystal structures, then it will be stronger, because a regular crystal arrangement is really strong. But it turns out that larger grains make it easier to bend a metal out of shape. To see why, we need to look at what happens at the molecular level when you permanently deform a metal. It's called plastic deformation, when you permanently change the position of atoms. And you might theorize that when you permanently deform a metal, maybe the grains are sliding over each other, or they're breaking up into smaller grains or joining together. It's actually none of that. It turns out the most important thing when it comes to plastic deformation is imperfections in the crystal, specifically imperfections called dislocations. Dislocations come in a few different flavors, but generally speaking, they look a little bit like this. And it turns out that dislocations are easy to move. You can see why. If you look at the bonds around a dislocation, they're already quite strained, so you don't need much energy to break one of those bonds. So when you apply forces to a metal in different directions, these dislocations will move around in different directions, like this. The important thing is it takes less energy to move dislocations through a grain than it does to move grains against each other. That's why dislocations are sometimes called the carrier of plasticity in a metal. You might have thousands of dislocations within a single grain in a metal. So when you're bending it, you're causing those dislocations to glide through the grain. But crucially, when a dislocation gets to the edge of a grain, it can't go any further. It can't hop to the next grain. That's the end of its journey. So if your metal has small grains, then the dislocations within those grains won't have far to travel before their journey ends, before they reach a grain boundary. And on a macroscopic level, that means that your metal isn't very ductile. You can't plastically deform it very much. And if you keep applying force, then it's just going to fail in other ways. Whereas if you grow the size of your grains like we did here, then you're giving those dislocations further to travel. You're increasing the capacity of your metal to plastically deform before breaking. You're increasing the ductility of your metal. That's about the limit of what I can demonstrate with this model. And obviously it's an oversimplification of the whole field of metallurgy, because there are different ways to heat treat a metal with different results. What I've done is probably closest to annealing, but there's also tempering and quenching, and there's loads of different variables, like what temperature do you raise the metal to? Is it above or below the recrystallization temperature? How quickly or slowly do you let it cool down? And you get all these different properties. It's really, really interesting, and it's not something I can demonstrate with this model, but I found a couple of really good videos if you want to dive a bit deeper.
So to finish this up, we are looking at the analysis and extension on the lab report, and so hopefully that previous video that you just watched from Steve Mould will give you some indication of what's going on, as well as the little bits of reading in the previous part of the lab there where we talked about the heat treatment. I just want to leave you with a final visualization of what happens when you anneal something. So annealing was the first thing that we did, heating it up in a very slow manner and just letting it cool down gradually. Or when you did the tempering part where it was very, very hard, annealing is the slow gradual heating of the material to change the grain size. So I'm going to show you a video now that indicates what happens with annealing. And then at the end of that, that'll be the end of the lab video. So we're just going to start out here with a whole bunch of little crystal grains, and now we're going to add some thermal energy, some heat at a very slow rate, and let's watch how these crystals grow into another. So you should be thinking about how the properties of that metal are going to change in terms of its hardness as the size of the grains increases, and thus there are fewer and fewer grain boundaries. Are we making the metal softer or harder?